Okay, this is the final hour of Physics 1B for October 5th. And we're going to now actually solve some problems with this information that we've gotten so far. So this is the problem. It says, what is the average translational kinetic energy of an ideal gas molecule at 27 degrees Celsius? What is the total random translational kinetic energy? The total random translational kinetic energy of molecules in 1 mole of this gas. So the first part says of a single molecule. And then the second one is, what is the total random translational kinetic energy of the molecules in 1 mole? And then what is the Rms speed of oxygen molecules at this temperature? Those are all the things we want to find. Okay? All right. So, part A. Which equation are we going to use? The average translational kinetic energy of an ideal gas molecule at 27 degrees Celsius. Which one of these equations? Are we going to use this one? Or are we going to use this one? Let's put them down here so we can see them with the problem. So is it this one? Or is it this one? Which one are we going to use there for part A? The second one, yeah. So this is pretty simple to figure out the average translational kinetic energy of a single molecule. That's this equation here. So that's going to be just 3/2 times K times T. So it's 3/2. K is 1.38 times 10 to the negative 23. And this was in joules per atom times Kelvin. We will multiply that by the Kelvin temperature. 27 plus 273 is 300 Kelvin. You know, I'm looking back at something we did in the previous problem. This number that's really hot, 70 degrees Celsius. So I should have done something like closer to 27, but I think the answer would have been pretty similar. Anyway, I just noticed that looking at that. Okay, so can y'all calculate what this is right here? What do you get? And then the units are going to be joules per atom, right? Okay. What about part B? What is the total random translational kinetic energy of the molecules in 1 mole of this gas? How do I calculate that? There's kind of 2 ways to do it. We could either use the answer we got, or we could just use, I think, this equation, right? I think we just use this equation. So the translational kinetic energy total is equal to 3/2 multiplied by the number of moles, which is 1 mole. And then we multiply that by R, which is 8.31. We're using this equation. That's in joules per mole Kelvin. And then we multiply by the temperature T, which is 300 Kelvin. And we get some number. Call it 3740 joules. That's just going to be in joules because the moles and the kelvins are going to cancel. So 1 mole of gas at about 27 degrees Celsius has 3740 joules of energy in it, of an ideal gas. It doesn't even matter what type of gas it is in this case, as it turns out. Okay. Part C. What is the RMS speed of oxygen molecules at this temperature? So to get that, we need our other equation, which said that v squared, oh, well, not like that, oops, just that Vrms was equal to the square root of, I think it was 3RT over the molar mass, right? We'll scroll just a little bit here, but I think that was right. Yep, 3RT divided by the molar mass. And the molar mass of oxygen is 32 grams per mole. So if we take those numbers, Vrms is going to be 3 times 8.31 times 300 divided by the molar mass, and it's 32. We got to multiply that. So the molar mass is 32 grams per mole. So we have to convert that to kilograms per mole. There's an awful lot of K's here. You've got KB, you've got K to represent translational kinetic energy, you've got K for Kelvin, and you've got K for kilograms too. That is just overwhelming, the number of K's there are there. 483 meters per second. Did you square root it too? I wasn't finished writing that, but did you square root it too, Andrew? Okay, cool, thank you. All right, there you go. So again, just to kind of summarize where we've come from, we went through this whole derivation. It took like an entire hour of class to do this derivation, basically. So we started right here. And we got these, if you think about it, really simple relationships, right? I mean, these equations are super, super simple to use. All right, so whether you understand where they came from or not super important. Can you use them? Yeah, that's mostly what we're going to be, kind of grading you on your homework and stuff like that in this class. So, okay. Any questions? All right, and then there's this problem that is really just about kind of thinking about what we actually mean by RMS and average speeds. Okay. So it says 5 gas molecules have speeds of 500, 600, 700, 800, and 900 meters per second. We want to find what is the RMS speed and what is the average speed. Okay. Yeah, I think that's right. You have to be a little careful just with the way these questions get asked. I mean, there really were just 3, right? I tried to, yeah. So it's translational kinetic energy is 3/2 nRT, the RMS velocity, and then this one as well. So yeah, those are your 3 main equations. Yep, that were used in this problem here. Okay, so RMS speed. So we said that Vrms was equal to, you take the velocity squared, you average that, and then you take the square root. Okay? So how do we do that? Well, the velocity, here, let's write this down here. The velocity squared average would mean take all of our velocities and square them, so 500 squared, and add them up. And then divide by the total number you have. That's how you do averages, right? So there's 5. That's going to give us V squared average. And if I want Vrms, we'll just square root that. But let's do it in 2 steps. So this is going to be you guys can calculate yourselves too if you get it done faster than me. That'd be great. I have 510,000. Yeah. So this is 510,000. I didn't write the units in here, but it's meters per second squared. And then Vrms is going to be equal to the square root of that. Sure, because they're all meters per second, right? So if I take 500 meters per second and I square it, then I'm going to get meters squared per second squared. Our answer, when we take the square root, we won't have that anymore, right? So what's 5/10,000 square root? I don't know. 1,000,000 square root would be 1,000. This is going to be that divided by the square root of 2. So divide by 14. 1,000 goes into 14. I don't know. I don't know what that is. Let's see. We'll just put it in the calculator. I mean, this is so annoying. I need to just get a regular calculator so I don't have to unlock my phone every time. 51000 divided to the 0.5. All right, 714. And that's going to be meters per second. So that's the RMS speed. So what if the average speed? What would the average speed be? Well, V average is just going to be 500 plus 600 plus 700 plus 800. Actually, I think I know what it is. I think it's going to be 700. Right? Because this has to be 700, right? Because 500 plus 900 is 1,400, and 600 plus 800 is 1,400. So it's basically 7 times. This is the numerator's gonna be 3,500 divided by 5 is 700. So that's the average speed. That's the RMS speed. They're not the same thing. It's important to understand these are not the same. They are not the same thing. I wonder, is VRMS always greater than V average? Probably. I don't know, though. It might be different if these are decimals or something like this. I don't know. Pretty straightforward problem. This is just designed to get you to understand. Like, I was using this terminology of RMS just to give you an idea of it's not that complicated what it is. It's just a statistical thing where you're just calculating this, square the numbers, and then, yeah. Okay. Any questions about that? Probably not. All right, so final topic is what's called mean free path. That's what we want to talk about. Okay, so the goal here is to kind of get an idea of how far a gas molecule has to can travel before it interacts with before it hits another molecule. Okay, so in this, we're going to a kind of new idea where we're now going to assume that these particles are not point-like. Okay, we're going to assume that they're spherical, and we're going to assume that they collide with each other now. So we're taking a diversion from some of the assumptions we made, just to take you all the way back to what those assumptions were. They're right here. We made the assumption that they were point particles, and we made the assumption that basically they don't collide with each other. Now we're going to say, well, that's ridiculous. They do actually collide with each other, and what we want to calculate now is how far can they go on average before they have to interact with another molecule. I included this little picture right here as well because it gives you an idea of what it is that we're describing. So here's a crowd of people, and it says, if you try to walk through a crowd, your mean free path, which is the distance you can travel on average without running into another person, depends on how large the people are and how closely they are spaced, right? It's going to depend on the size of a person, and it's going to depend on how close together you are. So if you're in a really thick crowd where everyone's kind of shoulder to shoulder, you're bumping into people all the time. If instead you're walking around at like an outdoor event and people are spread out more, you're going to be able to walk farther before you collide with people. And we want to kind of get an idea for how that applies to gas molecules. And this idea is called the mean free path. All right, so we're going to do another derivation. We're going to get an equation that is pretty straightforward. So we're going to consider that our molecules have a radius little r, and our goal here is to kind of calculate how often do they collide. That's the first thing that we're going to do. That's the kind of first step, is how often do they collide? And we'll work backwards from that to get mean free path. All right. So we're going to say that there are n particles. So there's n total particles that are spherical in a volume V. So we've got some container, and the volume of the container is V, the total volume, and there are particles all inside of here. Little tiny particles, there's n of them inside of here. The particles are spherical, and the first thing we're going to do is we're going to assume that only one of the particles is moving, okay? We're going to assume that only one of the particles is moving, okay? So this guy right here is going to be the one we assume moving. So we're going to assume first only one particle moving. So this would be like, imagine you're walking through a crowd, but everybody else is standing still. This would be maybe like at a concert or something like that, where you're kind of like pushing your way to the front of the concert. Everybody else is staying in their places. You're just trying to get to the front. So we're assuming that only one particle is moving. Okay, one particle moving. And it's going to have the odds of encountering some of these other particles. Certain particles are going to be outside of its little sphere of movement. Okay, we're going to assume that it's moving to the right, and that we're going to look at particles that are contained within a cylindrical volume that has a radius 2r. And why is it 2r? Well, the idea would be that some of the molecules are outside of this little spherical volume. I'm sorry, of this cylindrical volume right here. But any particle that fits inside of here, like this one, where it has a radius r, which means it has a diameter of 2r, any particles that are inside of this cylindrical volume right here, the moving particle is going to interact with them, right? So it's going to collide with any particle within the volume. So any particle that's actually in the cylinder, it's going to collide with it. And when I say in, some particles are going to be partially in and partially out, but it's only the particles that are fully inside of here that we're guaranteed that it's going to interact with, right? You can imagine a particle, well, it's drawn up here, right? This particle only has some portion of its extension into the volume, so it's unlikely that this guy's actually going to hit this one, whereas this one's completely inside of there. All right, so the volume contained inside of here, V, is going to be equal to 4 pi r squared times V times dt. You take the area of the edge, which would be pi times the radius squared, but the radius is 2r, so the area of the end cap, A, would be 4 pi r squared, just because it has a radius of 2r. And the volume of that container then would be 4 pi r squared times V times d. And we know that there are n over V. This is the number of particles per unit volume. Effectively like the number density. Okay, so the number of particles that are actually inside of this cylinder then can anyone tell me, what would it be? The volume of our little container is this. In fact, I should probably call this something different. Let's call it V cylinder, because this V is the total volume. Okay, so how many particles would there be inside the cylinder? I could just take the number of particles per unit volume in general and then multiply by the size of the cylinder, right? So the number of particles per unit volume, we're going to call it dN. And we're going to say that it's equal to this times this, basically. Just the volume of the cylinder multiplied by the total density. So it's going to be equal to 4 pi r squared times v times dt, and then times the total number of particles in the system divided by the volume. And then we can say that since if we know the number of particles that exist in here, then we can find the number of collisions per unit time. By simply dividing the dt to the left-hand side. And we end up getting 4 pi r squared multiplied by the velocity. And there's still an n left over, actually, right? Oh yeah, n over v is still here. So v is velocity, by the way, and then we multiply by n and we divide by v, total volume. So v is the velocity of the particle. Now, we made the assumption to begin with that only one particle was moving, okay? And it turns out to be the case that if you want to include the effect of all the particles moving, then you're going to get another factor of square root 2. So we have to multiply this by square root 2, where that square root 2 takes into account all the particles moving. Your book just basically states this. I'm sure at some point in my life I learned where this comes from. I'm sure that if any of you really want to go dig, you can figure out why that's the case. But apparently the number of collisions is increased by about a factor of root 2 if you say that all the particles are moving. Do we want to think about why that is? What do y'all think? I'd encourage you, if you want to go read more about it, that you can. I probably should read more about it too, especially if I'm going to keep teaching 1B. But yeah, so if you take into account all the particles moving, we just need to multiply this thing by a factor of square root 2. All right, so that's the number of collisions per time, okay? And just to take you back to what we're doing here, we want to know how often they collide. We've done that, right? That's how often they collide. It's this number here. It's related to the velocity. It's related to the r, which is the radius of a molecule, and then it's related to the density. The more dense they are, the more often they're going to collide. The faster they're moving, the more often they're collide. The bigger they are, the more often they're going to collide, and there's some other factors. Hopefully, that should all seem reasonable, right? More closely dense, they collide more often. Again, think about people and a crowd. R represents like the size of a person, N over V is the density, and V is how fast people are moving, okay, so we got that, and what we can do is the mean time, all right, so what we can call T sub mean. The mean time between collisions is going to be the inverse of this. It's going to be dt over n, dn. So this is going to be equal to the inverse of all of this stuff right here, which is basically just volume divided by all the other stuff. So divided by 4 times the square root of 2 times pi r squared times, we have velocity, and we have the total number of molecules right there as well. So this would be the mean time between collisions. Okay. And then to find the mean free path, we would simply take this quantity and multiply by what? What will we multiply by? So to find the mean free path, velocity, that's exactly right, Mr. Mears. So to find the mean free path, which is what we were ultimately trying to figure out, the mean free path, how on average, the symbol that's used in your book for this is lambda. I don't know why it's lambda, but it should be equal to the velocity of the particles multiplied by the mean time between collisions. And that's going to be, you can see what's left over here. It's going to be volume divided by 4 root 2 multiplied by the cross-sectional area of a molecule, right? Pi r squared would be the cross-sectional area of a single molecule. Certainly a very small number, right? This has to be a really small number because we're talking about literally the radius of a single molecule right here. And then what's left? Big N is left over here. we can also write this in a slightly different way. So this is one. This is the version that your book has, like, kind of grayed out or grayed in. But we can use another equation here. We have volume and we have N. What equation relates volume, number of molecules, pressure, and temperature? We can use the ideal gas law, exactly. The ideal gas law is the one that tells us that if I take pressure and I multiply by volume, that's equal to either nRT or it's equal to big N times K times T. And since we already have big N in here, we might as well use this. So we have V over N, so we need to write V over N, but we can see then, I think, that volume, I should really write this like this, volume divided by N would be KT over P. Okay, I could have helped myself out if I... Yeah, V over N is KT over P. So that also means that the mean free path can be written in terms of pressure and temperature as, let's see, the numerator is going to be KT, and the denominator is going to be 4 root 2 pi r squared, and then times pressure. Is that right? KT over, yeah. Let's see if this equation makes any sense. All right, let's look at the one in red first. This says that mean free path is directly related to the volume. So that makes sense. If you've got a big volume, you've got a lot of space to move in, right? And that means the particles can travel on average pretty far without actually interacting with anything. It depends on the cross-sectional area of the molecules. That should make sense because the molecules have to actually, they have to actually be able to hit each other. So if the radius is really small, then the mean free path is going to be big. If the radius is large, it's going to be relatively smaller. It's also inversely proportional to the number of molecules. Why would that be? Why would it be inversely? If you have a lot of molecules, what happens to the mean free path? Things are squished together, right? There's less space to move around in. Exactly, it's more dense, right? You can think about N over V is basically density, if you think about it. Okay, let's see if this one makes sense. The size of the mean free path is proportional to temperature. The hotter the gas is, the farther the molecules are going to be able to move. Why would that be? Hotter the gas is, the farther they can move. Why would that be the case? They move faster, exactly. This is what we learned today. There you go, they have more kinetic energy, exactly. So you guys, we learned something today. Temperature and kinetic energy, they're connected to each other. I gotta be honest, only thing I remember from studying thermodynamics about gas molecules is that temperature and kinetic energy are related to each other. If you can remember that idea, you can kind of work your way through a lot of the other stuff. It says it's also inversely proportional to pressure. So if the pressure is really high, then the mean free path is going to be short. And if the pressure is low, well, then the mean free path is going to be larger. Okay, less pressure. These things, they're all connected to each other, right? That's one of the things that's interesting about this is that, temperature is directly connected to velocity. We figured that out. Pressure was actually related to velocity too, right? There was our pressure relationship, right? The pressure is going to be related to, there should be like a 1/3 here and V average if you want to really do this right. I guess that's right here. Yeah, the pressure is connected to the velocity, but it's also connected to the density, right? So it's kind of hard to, for me personally, it's hard for me to disconnect pressure and think about pressure without also thinking about the density within the space as well. Because high pressure is going to mean that there's a lot of density. Yeah, so. Okay, well, let's do this problem, and let's actually see what these values are like. Like how big is the actual mean free path? It's got to be really small, right? No, sorry, it's got to be. The fact that there's a radius in here means that this number is going to be. We'll see. Also, K. I mean, K is 10 to the negative 23. this distance is going to be, I would guess, very tiny. I don't know though. Let's see. All right. So estimate the mean free path of a molecule of air at 27 degrees Celsius in 1 atmosphere. Model the molecules as spheres with a radius of 2 times 10 to the negative 10 meters. Estimate the mean free time of an oxygen molecule with a velocity of Vrms at 27 degrees Celsius and 1 atmosphere. Do y'all want to try this? Do y'all want to just try to do the calculation? Should be pretty easy, right? Okay. Remember that for temperature, you're going to use 300 Kelvin in this case. I don't know, take a few minutes, see if you guys can solve it. Okay, does anyone get an answer yet?
all those numbers, plug them in this equation. I got something times 10 to the negative 8. Is that what you got? I think that's what I got too. Let's see. Oh my god. 5.75 times 10 to the negative 8. That's what I got. Yep. So we plug these numbers in. It's going to be that times 300. And then divided by 4 times square root 2 times pi. Multiply by the radius squared, which is 2 times 10 to the negative 10 meters whole squared. And then what's left? Pressure. Then multiply by 10 to the 18. Did you put in 10 to the positive 23, Ruja? Is that what you did? Or you're off by exactly a factor of 10. No, not 10. 20. That's 18 minus negative 8. Oh my god, I can't do it. No. 18 minus 8. You put negative 23 for the exponent of the radius. There you go. Okay. So 2 times 10 to the negative 10 meters squared. Multiply by pressure. Got to put pressure into pascals. And this gives you about 5.75 and 10 to the minus 8. Is 10 to the negative 8 an angstrom? Is that an angstrom? 10 to the negative 8? I don't remember. So that's your mean free path. Not very far. It's about 100 times as big as the size of the atom, though. So they can move about, 100 times. Is the angstrom 10 to the negative 10? I kind of forget sometimes. So these molecules can move about... angstrom is negative 9, huh? Okay, that's... all right. So these molecules can move about 100 times as far as their radius without actually running into anything, if that gives you an idea about... So what does this tell us? It kind of tells you, kind of how far apart they are in a way, right? Not exactly how far apart they are, but, on average, how far they travel before they interact with each other. So it does give you some semblance of just the spacing, I think, to some extent. Maybe, okay, angstrom is 10 to negative 10. That's reasonable. So that's the mean free path in this case. And then part B says to estimate the mean free time. Well, we can do that just from here. But we have to do, okay, you got 9.75 10 to the negative 14. Anybody else get the same thing? So we got to find Vrms first, right? So we would take Vrms of a molecule is going to be 3 times RT over molar mass. So it's 3 times 8.31 joules per mole Kelvin. And then we got to multiply that by the temperature, which is 300. We have to divide that by the molar mass of oxygen. So that'll give us the arm. I feel like we already did this calculation, right? The previous problem? Yeah, 483 is the Vrms. And then to find T mean, we would take lambda divided by the velocity. So 5.75 times 10 to the negative 8 meters over 483 meters per second. So T mean would be I got 1.2 times 10 to the negative 10. Which would be something like 0.12 nanoseconds. That is not very long. You calculated. Did you use a different value for velocity, Kenny? Okay, so that's when you think about what we did today, we were able to not only figure out how fast the molecules move, we get an idea for how spaced out they are, right? They're pretty clumped together from our perspective, but from the perspective of an individual molecule, there's still a lot of distance between them, because it's about a factor of 100 difference between the radius of the molecule and how far apart they are. We see that the mean time for collisions to occur, that's basically what this means, is how often the collisions occur, is once every 0.1 nanoseconds, or 10 times every nanosecond, right? So that's what the rate of collision would be, that there's 10 collisions every nanosecond. And that seems like a lot of collisions. But when you think about the fact that if you have a mole of these atoms, you've got 10 to the 23 atoms, and they're only interacting 10 times every nanosecond. That means there's a whole lot of them that are probably not interacting with each other, right? At least not very frequently. If it's 10 times every nanosecond, it means 10 billion times every second, right? But there's 10 to the 23, which is like a billion times a billion times a billion, or at least close to it. Not exactly. So you've got some large fraction of your molecules that are not interacting very frequently, right? So I think this kind of, maybe I'm reading too much into this, but like just looking at these numbers for me, it kind of verifies the ideas that we used to begin with the ideal gas, to take that back to there, which is that the molecules effectively behave like point particles that are small compared to the size of the container and the average distance between the molecules. That is true, from a factor of like 1 to 100 in terms of the average distance that we basically just kind of calculated. It's not true that they're point particles, but I think the assumptions we made are reasonable based on kind of knowing something about what the real numbers are now. I don't know what y'all think. Okay, so you guys, I'm not being crazy. Okay. So I have one other thing I wanted to talk about today, which is heat capacities, but we didn't quite get there. I will say you can read about it, but we'll talk about it next week, and then we'll move into thermodynamics. One thing to mention is I want to go back to an equation just to kind of finish this up right here. This equation right here. So within this equation, where did that 3 come from? Do you remember? If we think back to the calculation that we're doing, where did the 3 come from in this equation? Where did that come from? If we go back through here, where did that 3 show up first time? Do you remember? It was pretty subtle. 3 directions that molecules can travel. Exactly, Dawes. It's very good of you to pick up on that. Exactly. We said that we could split up average velocity into these individual pieces, but then we said, oh, well, x, y, and z are no different from each other, so the average velocities in those directions should be the same, which allowed us to do this right here. 3 directions that molecules can travel. I like the way you said that, Dawes, because what we're going to be talking about next time is that this 3, it comes from the number of degrees of freedom that the molecule has, okay? We were talking about point-like particles, and point-like particles have 3 degrees of freedom, okay? They can oscillate in the x direction, the y direction, and the z direction. But what if we consider a molecule like a molecule of oxygen that's more like, let's say, a barbell? It's going to have 2 extra degrees of freedom, because not only can it move in the x, y, and z directions, but it can also roll along its axis, right? It can also, well, roll out. It can spin. So that's another degree of freedom. And it has an additional degree of freedom in the sense that the molecule can be springy. It can vibrate in and out along its axis, basically. And that means that for molecules like that, they're going to have 5 degrees of freedom, and that's directly going to affect their heat capacities. Because the heat capacity of a molecule, when you talk about a gas molecule, it's a little more complicated than the old
Q equal to mc delta T equation, okay? Gas molecules are going to have a different specific heat if you're talking about constant volume. They're going to have a different specific heat if you're talking about constant pressure. And they're going to be related to these number of degrees of freedom. And yeah, it's Chem 1B all over again, I'm sure. I'm sure you've talked about a lot about these things in your chemistry classes. Did you talk about like molar specific heat of a gas and stuff? I'm sure you did. That sounds like chemistry stuff for sure. Right. No, we don't even have to do that. So it's even simpler than that. We just put a 5 in front of it. That's it. It's just the fraction will change. And as he's mentioning, it's like there's dimolecular and there's trimolecular, and sometimes it's 5 halves and 7 halves, exactly. So it's either going to be 3 halves, 5 halves, 7 halves, and that's going to cover most of the molecules. And I believe it's kind of an estimation, but it's a really good estimation as I understand it, because you still have to like measure some of this stuff, but it turns out to be a really good estimation. CP and CV, right? That's going to represent the molar specific heat at constant pressure and the molar specific heat at constant volume. So you're going to have 2 different values for those things. And we'll see as we go on in this class that these things that we talk about, like, they're eventually going to be related to like things like entropy. So, everything, like with anything in physics, everything builds. And so, yeah. Anyway, I'm going to stop there because it's 1:05. I believe that's the time our class ends.